physical science time. But I got a Pascal, so slightly different. So let's, we're going to try to do this fast, even faster, but let's start with this word in the middle. I could have made it a little bit fancier. Oh man, this is going to look like butt because I didn't do it right from the beginning, but oh golly, look at this one. Well, I spent the first 4.5 minutes of the video trying to make this word prettier and it's now uglier. This is the word matter, right? What is matter? Someone give me your freshman understanding of what matter is. It is made of that. He's pointing at the periodic table.
Everything.
Not everything. Everything that takes up space and what else must it do to be matter? Has mass. So write that down. I'm not going to have room on my concept map on the board. But you write it down. Matter is defined as anything that takes up space and has mass. We could reduce that a little bit further. We could distill that a little bit further by saying it has mass and what? If it takes up space, what property does it have? Volume. So matter has mass and volume. So that's a fine definition. We're going to break up matter into 3 different ways. We just talked about, well, we're going to break up matter into 2 different ways. We talked about a third, which is, you pointed at it, all the elements, right? Matter can be classified by what element it is. But as we're about to see, not all matter is only one element. In fact, very, very little matter that we interact with on a daily basis is only one element. So the first thing, we're going to break up matter in this way. Matter is made of what? Matter can be considered an element, like we just said. But as we just said, not all stuff is made out of just elements. In fact, very little stuff that we interact with is a pure element. My wedding ring is something called white gold. It's an alloy, a mixture of the element gold and the element rhodium. But it's not a pure element, right? What else? So what other kinds of matter are around us? Very little pure element. Can you think of even an example of even one pure element around us? This is polyacrylate, which is not an element. What's an example of a pure element we might interact with on a daily basis?
Hydrogen, oxygen.
Hydrogen and oxygen, right? So you probably don't interact with hydrogen on a daily basis, but you certainly do breathe in. Even what you're breathing in, air is not pure oxygen. But you could get a tank of almost pure oxygen. You could get a tank of almost pure hydrogen. Is there anything that we do interact with that's not necessarily pure, but we consider it to be just one element? A lot of metals, for instance, like if you have iron file or an iron rake or an iron shovel head, right? Those things we might consider to be pure iron. Probably if you go to like the hardware store and you buy a rake, it's probably not iron. I would hope not, because it would be really heavy and not very useful because it would rust. But like a gold wedding ring, right? My wedding ring's not gold, but people do have gold wedding rings. They sometimes might even call it 24 karat gold, right? That's almost pure gold, right? We could find in the laboratory almost pure silver, right? Almost pure copper. The metals are fairly easy to find a pure element example of. But matter can be a pure element. What else can matter be?
Substance.
A substance. Well, let's be a little more specific because pure substances can include elements. So it can be what?
Liquid.
These are both substances. Substances are elements or compound. Let's call it a compound. So a compound is when we have, and you should write this down. Like I said, I'm not going to have room. But an element is a pure chemical element, right? It's basically, it's made up of what that are all the same? Atoms. All the same. So it has all the same kind of atoms. In a compound, I just told you I'm not going to write it down, but I actually am. The atoms aren't all the same, but the atoms are in the same ratio. So it has more than one atom, but they're in the same ratio, and they're bonded together in the same way. Atoms bonded, let's put that. Atoms bonded in the same ratio. So give me an example of a compound. Water. Water. Well, I don't know what that is, but it's got water in it. Water. And can we say what something we can always say for a compound is its chemical formula. What's the chemical formula of water? You know it.
H2O.
H2O. Give me an example of an element. So we can have an example here. Zinc. Zinc. Let's put zinc because I like that one. Zinc. Look, zinc, just an element. Water, two elements, right?
H2O.
Hydrogen and oxygen are two different elements, but they're combined in a certain ratio. And what is the ratio of hydrogen to oxygen?
Every 2 hydrogen atoms, there's 1 oxygen.
Exactly. So the ratio of hydrogen to oxygen is 2 to 1. This little baby 2 goes to the one before it, right? So there are 2 hydrogens for every 1 oxygen. If an if a substance, let me start over. If matter is not an element and it's not a compound, what else could it be? A mixture. A mixture. Air is a mixture, right? We were tempted to say earlier that air is made of oxygen, which is an element. It's not entirely made of oxygen. It's a mixture of different gases. Hey.
Can I go get olive oil? Sweet.
Within mixtures, we have 2 different types. What are they?
Solution. Heterogeneous and homogeneous.
Heterogeneous and homogeneous. The way you can remember this is super easy. Hetero means different, homo means the same, in the same way that heterosexual is someone who prefers the sex different from them, and homosexual is someone who prefers the sex the same as them. So hetero means different, and homo means the same. And so how does this relate to our mixtures? What might genius mean? What do you think is the root word of that? It has the same root word as like genetics or genes. It has the same root word as genesis. What might it be? It's gen, but what does it mean? Made up, like the beginning of stuff. Stuff, how it begins, how it arises, how it forms. So this is basically, we can think of it this way. Made of stuff that's different, and this is made of stuff that's the same. We haven't really talked about this quite yet, but we will. But we can think of heterogeneous mixtures as those that we can tell the different parts from each other. Usually they're in different states of matter. Different states of matter. But the point is we must be able to, I wouldn't say visually, but we can discern, let's just put that, discern the different parts. We can tell the parts apart. What's an example of a heterogeneous mixture? Depending on the concrete. You might mean like if we normally think of concrete which has like chunks of rock in it, right? We can tell the difference between the rock and the cement that makes up the rest of the matrix, right? So concrete's a fine example. As long as we remember that it has those chunks of rock in it. That's what makes it a heterogeneous mixture. What else?
Oil and water.
Oil and water together make a heterogeneous mixture. Even though those are both liquids, right? They don't combine. We can tell them apart. What else? Is there another example we can think of?
Like salad dressing.
Salad dressing. That's the very classic example. Salad dressing. Specifically like Italian salad dressing, right? With the different chunks, and there's oil and vinegar, so those don't mix, and there's chunks in it, so those don't mix in. The chunks are solid, the oil and vinegar are liquid, so yeah, salad dressing is kind of the classic example of a heterogeneous mixture. In your assignments that you've either done or will do, you'll be called on to give some more examples, so we'll leave that at that. What are some so if a heterogeneous mixture was one where we could discern the different parts, that obviously implies the homogeneous one is one where, yeah, we can't, so we're unable to discern. Unable to discern different parts. It still has to be made up of more than one thing, right? Otherwise it's not a mixture. Give me an example of a homogeneous mixture. We sometimes also call these solutions. That's another word for a homogeneous mixture, is a solution.
Water and water.
Coffee and creamer.
When you mix
Hold on
them,
for a
when you
second.
mix them, it's on
Yeah,
It's not a new substance. They're still the same thing, but they are.
ketchup and ranch.
It depends on the creamer, I would say. It depends on the creamer, but it might be coffee and creamer. Ketchup and ranch, that's disgusting. We're not going to talk about that because it's still going to have the little floaties of like dill and parsley and stuff. Too complicated. Vinegar and what? Just vinegar. Vinegar, which is acetic acid dissolved in water, right? Salt water, the saline solution you might put in your eyes for your contact lenses, that's salt dissolved in water. Oh, I was just checking to see if the mic was on. I think it is. I think the mic is on. Boy, that would be, I would hate that. But anyway, so for example, we're going to put here, let's just put vinegar, which is acetic acid dissolved in water. Have you lately, well, I guess it was like 2 weeks ago now because I was gone, have you made a solution in the laboratory, for instance?
Yes, the food dye.
Yeah, food dye in water would be a homogeneous mixture. Because the parts would still be, it's still food dye and it's still water, and we can even separate them. We saw how to separate them. But we are unable to discern. Like you can't like point at, oh, here's where the food dye is, here's where the water is. Whereas with this, with the concrete, here's where the rock is, here's where the concrete is. Do you see what I mean? That's what this discern means, is that we can identify the different bits. Questions about any of that so far? Your book, and if you don't have your book, you can look online. But your book goes on kind of at length to describe the different ways that we can separate mixtures. So for instance, distillation, that's what we did in the lab. Distillation is where we separate them based on their boiling thing, right? So one would boil at a different temperature than the other, excuse me, and so we could separate them that way. All mixtures can be separated by physical means, right? Distillation, when we boil something, that's a physical change, right? What, as opposed to what? What else would we talk about if we weren't talking about physical changes? We would be talking about chemical changes. So let's write real quick in this little box over here. I'm going to write chemical versus physical changes. In a chemical change, what happens?
A chemical reaction happens.
In a chemical change, yeah, a chemical reaction happens. But what of these things might be different? Will the elements be different afterward?
No.
Probably not. But they will be different substances, right? They'll be different, they will be different compounds. In a chemical change, compounds change. In a physical change, what can change in a physical change? State. That one's a really important one that people sometimes get confused about. But if the state of matter changes, that's only a physical change. If an ice cube melts, that's a physical change. What else can change in a physical change?
Color.
Possibly, yeah. If we paint something or if we dye something, color can change. Shape can change, right? If I have a carrot and I cut it in half, it's still a carrot, just cut in half, right? It's shape change. I don't know how legible this is, but basically in a chemical change, the compounds, what it's made out of changes. In a physical change, only its state, color, some other things, but it's something physical about it. One of its physical properties changes. Can physical and chemical changes occur together? Yeah, definitely. But in that case, we would still call it a chemical change, right? So for instance, if I mix up some chemicals and it changes color, but also the compounds change, it's both a physical change and a chemical change. So we would still call it a chemical change. Questions about any of this? And when I say physical versus chemical properties, you know what I'm talking about, right? Basically, physical properties are those that we can observe without changing what it is, and chemical properties are those that determine how it changes. For instance, if something is flammable, that's a chemical property that tells us how it's going to react. If something will dissolve in acid, or if something will react with acid, that's a chemical property because that tells us how it will react.
What is that first word for physical change?
State.
Okay.
Speaking of state, let's talk about another way we can break up. Yeah, just get out of here. Sorry, Kira. Speaking of states, there's another way we can break up matter, right? So we broke it up into whether it's element, compound, mixture, but we can also break up matter. All of matter can be classified by state. So what are the states of matter? Give me 4 of them.
Solid,
liquid,
gas,
plasma.
Good.
plasma.
I want you to list them in that order, because I'm going to change colors here and we're going to talk about how they change one to the other. If you had to guess what you do, because I'm making you, or you might already know, because you read it on your own, which of these 4 things has the least energy? For a given substance that can exist in all 4 of these, which one has the least energy? Solid. Solid has the least energy. So as we add energy to a solid, what happens?
Melts.
It melts. So this process of solid becoming a liquid is called melting.
Like ice.
Like water that's solid
Water vapor.
turning into water that's liquid. So for a given substance, this would have the lowest energy, and the plasma would have the highest energy. Now what we're going to do is we're going to go through, and as we add energy, we're going to tell what that process is that changes one to the other. So solid turning into a liquid is called melted. You're aware of melting. Liquid turning to gas?
Vaporizing.
Good. Vaporization.
Super.
And do you know what it's called when a gas turns into a plasma? I'd be kind of surprised if you don't. I don't think your book tells about it.
No, I didn't.
We call this
Maybe.
ionization. We have talked about it before, but this is called ionization. Do you remember, we did this back when we talked about electric fields, but do you remember what I said happens when a gas turns into a plasma? Basically, it has enough energy, it has so much energy that the electrons can be separated from the nucleus. In fact, they are separated from the nucleus, right? So now instead of having atoms of the elements, the very atom itself breaks up, and now there are nucleons and electrons floating around, and they're charged, and so plasma has a charge. They've been ionized. The electrons have separated from the nucleus. Okay? This has the most energy, right? Obviously, it takes a lot more energy to do that than to change a liquid to a gas, for instance. Now let's go the other direction. I'm going to do this in purple. I don't know that there's a specific word for plasma to gas, but I'm going to call it deionization. What do we call it when a gas turns to a liquid?
Oh.
Condensation.
Condensation. This is becoming kind of a messy chart, but I like it anyway. And then when a liquid becomes a solid? Freezing. And for a given substance, these two processes occur at the same temperature. And these two processes occur at the same temperature. And I don't specifically know, but I would assume these two processes occur at the same temperature. Why do we concern ourselves with temperature when we're talking about energy? Like,
Because the higher the temperature, the faster the
exactly.
energy.
Exactly that. Because when we're talking about particles, we're talking about atoms, the higher their thermal energy, the higher their temperature, the faster the particles are moving and the more freedom they have to move.
That's correct.
So these things each have the same temperature. What temperature, do you know, does water freeze at?
32.
32 degrees Fahrenheit. And in Celsius?
0.
0. Write that down somewhere. You do need to know that. Yes, Peyton.
Plasma to a gas is called recombination.
Very interesting. Payne says that plasma to a gas is called recombination. I like that better, so rewrite it as that. But the temperature in degrees Celsius, thank you, Payne. The temperature in degrees Celsius that this happens, that freezing occurs, is 0. But also, that's the temperature at which it melts. It's the same. You see? What about for this, when a liquid turns to a gas? What temperature does that happen at for water?
212 degrees Fahrenheit.
212 degrees Fahrenheit, and in degrees Celsius?
100.
100. And then can you guess at what temperature would that same gas condense?
100.
100. It's the same. It has to be the same. Thank you, Peyton. Does that make sense?
What is it vaporized as? I'm writing this down. At what temperature?
For water, it's 100 degrees Celsius.
Okay.
What are the particles doing in here? In a solid, what verb do we use to tell what the particles are doing? You might have read. I'm going to make this even messier. Let's do that in green too. What are the particles up to in a solid? Are they moving?
They're solid.
They're moving, but they're moving how?
Vibrating.
They're vibrating. They're oscillating. They're only moving in place. They're vibrating. We can think about the particles in a solid kind of like you little children's in this room, right? You are moving. I can see you writing and breathing and flopping about, but you're in your same little spot, right? In a liquid, however, what are they doing in a liquid? What are the atoms doing in a liquid?
They go back and forth.
They did that in a solid too, though. They're what?
They're free.
They're free to do what?
They pass each other.
They can move past each other. They can slide around past each other. They can flow past each other. Flow. That would be like, what would that look like if you guys were the atoms making up a liquid?
We were just moving.
Yeah, like if you're like snakily, right, you're still kind of confined to the same spot, but you're just kind of sliding past each other. That would be gross. Let's not do that one. In a gas, what do you reckon they're doing?
Running around.
Yeah. We say they are bouncing. They are bouncing not only off of each other, which they are, but off of the walls of their container. That'd be like if you guys were just sprinting at top speed, crashing into the wall and bouncing straight back and doing that with each other too. Just chaos, just pandemonium. And you can tell, obviously, if that were the case, I would be furious. But also, this would require a lot more energy from you than this, right? You can see how the more energy these things have, the more they can move. And then when there's plasma, this would be like if you're moving so fast, your like limbs are flying off and they're bouncing. So
That's creepy.
a lot. So I don't know why I'm gonna put that one. Bouncing in pieces. Let's make it real metal. In pieces. They have so much energy they've flown apart, right? This is kind of turned into a bad illustration, but hopefully it makes it
Which
worthwhile.
apparently is the best illustration ever.
I'm going to end this video here because I think this all kind of fits neatly together. Basically what we talked about down here is how we classify matter by its composition and what the physical and chemical properties and changes of substances include. This was largely vocabulary. And then up here we talked about how we classify matter based on its state of matter and the interactions therewith. You have questions about this bottom thing first? What chapter was this? 15. This time here was chapter 15. There was more to chapter 15, I hope you read it, I hope you will read it. And then up here, this is 16. And there's certainly more to chapter 16 that we will talk about more. But we're going to leave it at that for now. Do you have questions about any of this? Oh, okay.
Bye.